We clearly missed the memo.
Yeah. Hey, don't show up on Friday. It's crazy.
Oh, no, we clearly missed it. I don't like to participate.
Hey, don't show up on Friday.
Oh, thank God. This, I don't know, there's three of us. It's so uncomfortable.
A private physics lesson.
Yeah. I don't know.
What if y'all worked at the shift?
Yeah.
That'd be great.
That's what's gonna happen. Yeah. Gonna come eat some food?
I think so.
Fuck yeah.
You know what I mean?
You can have my discount.
I love that.
Woo-hoo.
I'm gonna try your guys's Tom Yum because I found out that I like that.
Better?
I don't know. It's different. Well, I don't have a good enough opinion yet. So I gotta try yours and see. Tom Yum tastes like some I like the coconut flavor. I like it to be more of like. So
Yeah.
got one phone call yesterday that I got accepted to work in that.
That's.
So excited! I was really like jumping up and down there. Physics study or the chemistry study.
Oh, that's exciting. Good for you. What do you?
So it's gene modification in malaria and Staph aureus to find like their resistance determinants and hopefully target them to be able to make vaccines that they're not able to evolve to. So the whole malaria thing, and that would be like one of the craziest things to ever be a part of because that would literally be like worldwide.
Yeah.
Like it's huge. She's got a $1.5 million NIH grant for it. So like she's like close, which makes me think like, yeah, like, dude, if we can figure that out before I graduate, that would look incredible on my application. Yeah. Like, oh yeah, I helped end the malaria thing going on.
Yeah, that's
And
insane.
him too. We're working together.
Yeah, we are.
It's gonna
Wow.
be so fun.
That's
Fantastic.
Dude, it's so crazy. We could like literally get like huge from this. Dude.
Yeah,
Like
right.
especially if she's able to actually figure it out and like we're able to figure out something to combat that.
I would just be happy to have my name on a piece of paper.
That's what I'm
right?
saying, yeah. Like that
That's
would be
super
huge
cool.
for us. That would
Exactly.
be the biggest thing to put on an application ever. And I plan to like stay in her lab as long as I can.
Yeah.
So,
Are you staying here for the summer or are you heading out?
yeah, I live here, so
Okay, fair.
born and raised here. But are you going home for the summer?
Sure.
Sweet, dude.
All
Looks like
right,
it's gonna be us.
exactly.
Okay, so is it time? Okay, well, we have one more minute.
It's always time for physics.
Yeah, of course, that's the right expression. We have to start now. So before we start, midterm on chapters 21, 22, and 23, a week from Monday. So March 14th, right? A week from Monday. And I'm going to also email a practice test probably this weekend at some point. Again, want to remind you, you to keep track of the conceptual questions, especially those from the homework assignment, they're very important to show understanding about the material. So the material is well, it could be tricky because there are multiple simple concepts, but they're connected with each other. And if you miss one concept, everything falls apart. Okay, so knowing this, the midterm is set. Oh, one more remark. Midterms, I have to enter some midterm grades, and we don't have enough information to have a reliable grade. So this means that any grade that is different from F or D or C, you have to take it with a grain of salt. So only if your grade is C or lower, in that case, well, you have to talk with me as soon as possible to see what's happening. Basically, there are a few people that are registered for the class, but never did a midterm, never even stopped doing homework assignments, but they are still registered. We have several of those. So those are usually the people that are going to get a grade that requires attention. Yes.
Question. So will you also post email the slides from the?
Yes, I'm going to. Okay, I'm going to send some conceptual questions, but so for the moment, focus on the conceptual questions that are from the homework assignments and from the practice test. I haven't written the practice test yet, so I don't know how many conceptual questions are going to be there, but focus on them and don't worry about on-screen quiz questions. If necessary, I'm going to email them to everybody. Okay, other questions? Okay, so now last time we started with two simple circuits. One of them was a resistor connected with AC voltage of the time. Voltage as a function of time is amplitude of some voltage times sine of 2 pi frequency multiplied by time. And we analyze this circuit by looking at the voltage and the current and the power consumed, and we represented the results of this using introduced phasor diagrams. So a different tool that we're only going to use in this chapter. So the results look like this. The voltage as a function of time, of course, is a sine function by definition. So it looks like this. The current as a function of time looks pretty much the same because voltage and current are connected. They are proportional to each other. The coefficient of proportionality is the resistance of the resistor. So the current is probably going to look something like this. So this is current as a function of time in sync with the voltage. And the power consumed in this circuit as a function of time is going to look like this. The power, average power, well, instantaneous power actually, is going to be like this. Because power is voltage multiplied by current. So here you have positive voltage, positive current, a positive power consumed. Here you have negative voltage, but also negative current. Their product is a positive power consumed. So this is the power as a function of time. Time and time on the horizontal axis. So the resistance is independent of the frequency. It has always the same value, no matter what frequency you are giving with the generator. So it is a fixed number, a constant. In other words, if you look at frequency and resistance here, it is some constant value of the resistance as a function of frequency. But the new part was the phasor diagram. And the phasor diagram actually is important because it is easy way to describe a relatively complicated situation. In this case, you represent the voltage with a phasor like this. So something like a vector that starts here from the origin of the phasor diagram and has the amplitude of the voltage that you have. But this vector-like phasor is spinning in counterclockwise direction with frequency, whatever the frequency is. And at any moment of time, the value of the voltage provided by the generator is going to be sine amplitude times sine, and amplitude multiplied by sine is this length. So this is the instantaneous value of the voltage at this instant. At the later moment of time, the phasor spins. Maybe it comes, let's say, here. And therefore, you're going to get this value for the instantaneous value of the voltage, because the angle is going to increase and get up to here, and so on. So this circuit is the simplest circuit because the current that is flowing in this circuit is represented with a phasor that is right on top of the voltage phasor. So this is the amplitude of the current, and the amplitude of the current is at any moment of time is the value of the current at any moment of time, again, is given with the sine of the angle multiplied by the value of the amplitude of the current. Here is the amplitude right here, why not? So we talked about this, but this is a summary of what we said. The things get a little bit more interesting when you have a circuit that has a capacitor and the same AC power supply. So capacitor with capacitance C, the voltage is again exactly V naught multiplied by sine of 2 pi ft. And last time we made the argument that, well, in this case, you have the voltage, of course, is whatever is generated from the generator. So it looks like a sine function like this. The current, though, is not exactly in sync, but it is out of sync with the voltage. So we made the argument that the current as a function of time is leading the voltage. So this means that right here, this means that the current starts when the voltage is minimum, you have maximum current, and after that it drops. When the voltage reaches its maximum, the current becomes 0, and so on. So you have, again, a function that resembles a sine function, but actually, it is shifted with respect to the voltage by a quarter of a period. And actually, if you look here, in that case, the voltage and the current would look the same way if you start looking from this point. And this is why we say that the current leads the voltage, right? It is ahead of the voltage by this amount, by this time interval, by a quarter of a period, or 90 degree. Well, the power consumed in the circuit, is 0. So the power E is, well, actually, it is not constantly 0, but half of the time it is positive power, because here you have positive voltage, positive current. Their product is the power, and at that moment of time, you're going to have some positive power consumption. But at the next moment, at the next quarter of the period, right here, and so I messed up the drawing badly. On the next quarter, well, let me redraw it because it is not drawn correctly. So you have the maximum when it is at 0 voltage, and the current goes to 0 when the voltage is at maximum, and so on. So it's at maximum here and minimum here, like this. So this is how it looks. Yeah. So the next quarter of the period, positive voltage, but negative current. Therefore, the power consumption in this quarter is going to be negative. And the result is that the average power consumed in this circuit that only contains a capacitor is 0. We said that something similar to Ohm's law is still valid. However, instead of resistance, you have an entity with dimension of ohms, the same dimension as resistance, but it is different because it is frequency dependent. And this is why we call it capacitive reactance. So Ohm's law is valid only for amplitudes of the voltage and current. Or it is valid for RMS values of the voltage and current. So, but Ohm's law is not valid for instantaneous values of the voltage and current. So if you write this would be wrong, because the voltage and the current are not in sync with each other, but then there is a shift of 90 degree with respect. The current is 90 degree ahead of the voltage. So this is why instantaneous values are not given with a simple expression similar to Ohm's law. Only RMS values and amplitudes. So, and well, Ohm's law here is valid for any value, instantaneous value, amplitude, RMS. So anything that you want, Ohm's law works here. Okay, frequency dependence of the capacitive reactance. Well, it looks like this. The capacitive reactance is equal to 1/2 by the frequency times the capacitance. So this means that the capacitive reactance as a function of frequency looks like this. Looks like a hyperbola with asymptotes. When the frequency is very high, the capacitive resistance, capacitive reactance is 0. And when the frequency is close to 0, the resistance, capacitive reactance is very large, infinite. And again, the important and more difficult diagram is the phasor representation of this circuit. So if at some moment of time the voltage is given with this phasor, in other words, this is the angle 2 pi ft, the current in the circuit leads this voltage. So the current is represented with a phasor that is ahead of the voltage by 90 degrees. And again, those two phasors are rotating with frequency f. And the last simple circuit that we have to analyze is a circuit that contains an inductor with inductance L connected again to AC power supply of the same type. V as a function of time is equal to amplitude V naught times sine of 2 pi ft. Well, what happens in this case is that, again, the voltage is whatever is provided by the generator. Let's say the voltage as a function of time looks like a standard sine function. However, in this case, the current is going to be out of sync. And according to, so how does the current change depends upon, well, it is dictated by Faraday's law of induction. So the Faraday's law of induction says that the induced EMF, the induced voltage in the circuit, is proportional to the rate of change, of the magnetic flux. Well, the magnetic flux is highest when the voltage provided by the generator changes fastest. And the sine function, we know that the sine function changes fastest when it goes to the 0 points. Well, it is changing the slowest when it goes through a minimum or a maximum. So when you put all those things together and take into account the minus algebraic sign in the Faraday's law of induction, you can convince yourself that the current as a function of time is shifted by a quarter of a period, by 90 degrees with respect to the voltage, and it lags behind the voltage by 90 degrees. So this means that the current changes like this. So it's here you have the largest current, and the current becomes 0 when the voltage is highest, and after that it increases and reaches maximum value when the voltage goes to 0, and so on. So you have a diagram that looks like this. This, and so on. So it again looks like a sine function, but that sine function leads the voltage by 90 degrees, by a quarter of a period. And you can see it if you mentally look at negative times here for the voltage. And if you look at this, you have a graph that looks exactly like this one. In other words, the current is behind the voltage by a quarter of a period. Again, you have power consumed on average is again going to be 0, because here in the first quarter, positive voltage but negative current means that negative power is consumed by the inductor. This means that the inductor gives back energy to the generator. On the next quarter, you have positive voltage, positive current, positive consumption by the inductor, and so on. So half of the time, the inductor consumes energy from the generator, but the other half of the time, it returns it back to the generator, and on average, no power consumption in the circuit. Ohm's law, a version of Ohm's law, is valid again. So voltage is current times something like a resistance, but we call it inductive reactance because, again, it is frequency dependent. And something like Ohm's law holds again for amplitude of the voltage in the current, also for the RMS value of the voltage in the current. But it doesn't work for instantaneous values. In other words, voltage is not current times XL because the voltage and the current are shifted by a quarter of a period, by a quarter of a cycle. The frequency dependence of the inductive reactance looks like this. The inductive reactance XL is equal to 2 pi the frequency times the inductance. In other words, if this is the frequency on the horizontal axis and if this is XL, the inductive reactance, you have a linear dependence between them. So it is described with a straight line that goes through the origin of this coordinate system. And again, the phasor diagram is the difficult diagram in this reasoning. So if the voltage phasor looks like this, the current phasor lags behind. So remember that this phasor is spinning with frequency f. So the current phasor is lagging behind by 90 degrees. Here it's the 90-degree angle, and this is the current phasor lagging behind. Okay, and now let's see remarks, questions for the simple, well, everything is simple, but quite involved and multiple small details that sometimes actually, not sometimes, but all the time, you have to ask yourself question. Why with increase of frequency, you have increase of the inductive reactance? Why with increase of frequency, you have decrease of capacitive reactance? So those things require, well, multiple questions of this type. You have to ask yourself about questions of this type, and we have to discuss them if they are confusing, and they should be confusing because it is a complicated material. So the fact that, for example, with increase of frequency, you have increase of inductive reactance comes from the fact that increase of frequency means that higher rate of change of magnetic flux that is going through this inductance, and therefore you have higher back EMF induced, and therefore you have higher resistance. So what matters at this point is to be able to put all of this information together and summarize it for circuits that contain resistor, capacitor, and inductor. And let's try to do it now. Any remarks now, questions, things that come to mind before we start? I want to finish the chapter, and after that, we're going to do examples. And hopefully the examples are going to gradually clarify the situation. So now, well, we need all of those three cases, but I also need some Blackboard space. So I'm going to erase this and try to analyze the circuit that contains, well, we need more space. Let's see. Maybe this phasor is the simplest, so we can get rid of it. And now consider a circuit that contains, well, let's clean all of this space because you. And now consider the circuit with a resistor, a capacitor, and inductor connected in series with AC power supply. Again, the power supply gives voltage as a function of time is V naught times sine of 2 pi f t. So let's try to analyze the circuit using directly the phasor diagrams for the three cases that we analyzed so far. So the phasor that I just erased, plus the phasor here for the capacitive, and the phasor here for the inductive circuit. For the capacitive case, the voltage is across the capacitor. The current, of course, is a single current in the circuit, so I'm not going to label it. For the inductive circuit, the voltage is across the inductor, V naught L, if you want, two subscripts, so to keep track of everything. And the circuit that I erased, the voltage is across the resistor V naught R, let's say. So this means that, look, you have one voltage across the resistor, V naught R. You have another voltage across the capacitor, V naught C, and you have the third voltage across the inductor, V naught L. The phasor diagram representing those three voltages is going to look like this. Well, you're going to have some voltage across the resistor. V naught R, and the current is one single current in this circuit. So that current, we know from the phasor that I erased, that current is in sync with the voltage. So the current is going to be here, the phasor representing the current. Of course, this phasor spins, remember. Now, where is the phasor representing the capacitive reactance? Well, if you look here, the voltage across the capacitor is behind the current by a quarter of a cycle. In other words, here is the current, the voltage across the capacitor is going to be a phasor like this. V naught C is going to be 90 degrees behind. 90 degrees behind. So this is V naught across the capacitor, this one. Well, the voltage across the inductor is 90 degrees ahead of the current. So it is going to be right here. So this is V across the inductor, V naught L. So you see that the phasors across the inductor and across the capacitor are in opposite directions. And as a result of that, you can demonstrate that you can work with the phasors in a way similar to working with vectors. So you can immediately add those two vectors because they're in opposite directions. So addition of vectors in opposite direction gives you a vector with size equal to the difference of the two sizes. So the first step is add this and this because they are easy to add, they're in opposite directions. So the resulting phasor is going to look like this. So here it is V naught L minus V naught C. The voltage across the resistor is still the same. Let me try to do it exactly the way it was. So this is the voltage across the resistor, and of course, this is the current in sync with it. So now you have 90-degree difference between those two phasors, and you have to add those two phasors as if they're vectors. In other words, you have to take, let's say, this one, and draw a representative of that here, or representative here, like this. And the resulting phasor is going to be a phasor that looks like this. So this is the voltage V naught. That is the result. This is the voltage that is coming from the generator. In other words, it is the voltage across those 2 points, or those two, the same thing. So this is the total voltage that is generated in the circuit. So notice that the voltage and the current are shifted in phase by some angle phi. And one of the goals is going to be to figure out the value of the angle phi using this diagram. So keep in mind that this is a right triangle that is formed, right? This is a right triangle. And you can write a connection between the sides in this right triangle. So in this right triangle, the red vector, the red phasor, is the voltage in your circuit. So you can say that vector, the voltage squared has to be equal to the voltage across the resistor squared plus this voltage difference between the inductor and voltage across the capacitor, all of this squared. So this is the Pythagorean theorem for this triangle that is formed with the red hypotenuse, and the two sides are the voltages across the resistor, or the voltage difference between the voltage across the inductor and the capacitor. Now use the Pythagorean theorem. From the Pythagorean theorem, here is the Pythagorean theorem for the inductor. So this is V naught for the inductor. A similar expression you have for the voltage across the capacitor. Let me write those expressions. So the voltage across the resistor is the current multiplied by the resistance. The voltage across the capacitor is equal to current multiplied by capacitive reactance. And we're talking about instantaneous values, not instantaneous values, but amplitudes, voltage across the capacitor amplitude and current amplitude also. And the voltage across the inductor in a similar manner is related with the amplitude of the current times inductive reactance. So substitute, take amplitudes here and substitute V naught R with I naught times R. So you're going to get the total voltage squared is equal to the voltage, well, equal to the current amplitude squared multiplied by resistance, right? This is just Ohm's law. And after that, in the brackets, you have to have this minus this. So you're going to have current times inductive reactance minus current times capacitive reactance, everything squared. From here, on the right-hand side, you can factor out the common current squared, and you're going to get something like this. V naught squared is equal to I naught squared. Resistance is squared, of course, here. And in the brackets, you're going to have resistance squared plus inductive reactance minus capacitive reactance in brackets squared. Now take square root of both sides of this expression, and you're going to get that the voltage, total voltage amplitude, is equal to the current amplitude multiplied by square root of the expression in the square brackets. Square root of R squared plus XL minus XC squared. So this expression tells you that the voltage and the current amplitudes are proportional to each other, with coefficient of proportionality, the square root. This means that this square root acts like a total resistance of your circuit. And the expression, the square root expression is called impedance of this circuit. So you define impedance of the circuit as impedance Z is defined as square root of R squared plus XL minus XC in brackets squared. So this is the definition for impedance. And using that definition for impedance, you write an expression similar to Ohm's law for this relatively complicated circuit. Voltage amplitude is equal to current amplitude multiplied by impedance Z. So this is just like Ohm's law. Ohm's law was that current, voltage is current times resistance. So impedance plays the same role as resistance, but you cannot use resistance for a circuit that has inductors and capacitors. The impedance takes into account the presence of inductor and the capacitor in the circuit. Now, exactly the same reasoning could have been done, not with amplitudes of the voltage and the current, but with the RMS values instead of amplitudes. And the result would be voltage of your circuit, RMS value of that voltage, is equal to the RMS value of the current in your circuit multiplied by the impedance. However, you cannot say that instantaneous value of the voltage is equal to the instantaneous value of the current times impedance. This is not correct, because the voltage and the current are not in sync, but they are out of sync by this angle phi. So angle phi, of course, is important. Let's figure out the value of this angle phi. When you look at this right triangle, tangent of that angle phi is going to be equal to opposite side, which is V naught minus V naught L minus V naught C, divided by adjacent side, which is V naught R. And again, substitute every voltage with the analog of Ohm's law or the Ohm's law, and you're going to get current multiplied by inductive reactance minus current multiplied by capacitive reactance divided by current multiplied by resistance. Current amplitude cancels out everywhere, and you get that the tangent of the angle phi, the tangent of the phase difference between the voltage and the current is equal to inductive minus capacitive reactance divided by the resistance in the circuit. So this is one useful expression. So the angle phi is important. It tells you how much the voltage and current are out of sync. Well, in many problems, in state of tangent of the angle phi, you encounter cosine of the angle phi. And again, using the definition for a cosine of this angle, cosine is adjacent divided by hypotenuse. So cosine of phi is going to be, adjacent side is V naught R. The hypotenuse is V naught. And you know that V naught R from Ohm's law is I naught times resistance. And you know that V naught is I naught times the impedance. So again, you cancel the current and you get that cosine of the phase difference angle is equal to the resistance divided by the impedance. So this cosine of the angle is what we call power factor. And it is called power factor because it is going to appear in every relation that calculates the power consumed in your circuit. Let's calculate the power consumed in the circuit. Well, you can say that the power consumed by the circuit on average is equal to current squared RMS value multiplied by resistance. So this is one simple formula for expressing the average power consumed. But it is a formula that is similar to what we have encountered before for a circuit that only contains a resistor. But if you look at this formula that we just derived, the formula which says the cosine of phi is equal to R divided by Z, you can say that the resistance R is equal to impedance Z multiplied by cosine of the angle phi. And if you substitute that resistance here, you're going to get that the average power consumed is equal to RMS value of the current squared multiplied by impedance and multiplied by cosine of the angle phi. So here is a formula in which in order to calculate average consumed power, you need to know this power factor cosine of phi. And now remember that for power consumed, we had three formulas, different, that were useful in different cases. So if you take into account that voltage and power are connected with each other with this expression similar to Ohm's law, and this means that the current RMS value is equal to voltage RMS value divided by impedance. So if you substitute 1 power of the current with this expression, you're going to get that the average power consumed in the circuit is equal to current RMS value multiplied by voltage RMS value. You have Z, and you also have Z in denominator, they cancel out. So you are only left with the power factor cosine phi. So this is a second formula to calculate the average consumed power. And in a similar manner, if you replace this current with its equal, you're going to see that the average power consumed in the circuit is equal to RMS value squared of the voltage divided by impedance and again multiplied by cosine of phi. So you see that this cosine of phi appears in all three formulas that include the impedance and express the average power consumed in the circuit. So this is why this cosine of phi is called power factor. So look, it is a lot of information, boards filled with formulas, but you have to realize that the formulas that are important are practically analog of Ohm's law. Just in state of resistance, you have impedance. And, well, the formula similar to Ohm's law is only valid for amplitudes or RMS values of the voltage and current, but not valid for instantaneous values. Because the voltage and the current are shifted by angle phi that has this tangent or angle phi that has this cosine. So, once you start working on the homework assignment, and you have to do this as soon as possible, you're going to encounter questions, multiple questions, and in the process of answering those questions, you're going to make sense of the formulas that I just wrote on the board. Now, the last section of this chapter is related with a phenomenon called resonance. So this phenomenon investigates at what value of the frequency in the circuit you have maximum current. Well, look, the voltage is whatever voltage is given by the generator. So you're going to have maximum current if the value of the impedance is the smallest possible value. And if you look at the definition for impedance, smallest possible value is achieved when XL and XC are equal to each other. So XL equal to XC means you're going to have highest possible current in your circuit. In other words, XL was 2 pi frequency times inductance, and XC was 1 over 2 pi frequency times capacitance. So the frequency at which you're going to encounter the highest current is going to be solving this equation for frequency. You're going to get 1 over 2 pi square root of L times C. At this frequency, the current flowing in this circuit is going to have the highest possible value, and this is called resonance frequency. And this formula describes the circuit that is used in every radio or TV receiver. So the receiving circuit of a radio, for example, contains an inductor and a capacitor like this. And you can change the capacitance of the capacitor by rotating this knob. So you can change the value of the capacitance and you can tune to a particular frequency to a particular radio station. So we're going to talk about this resonance phenomenon in RCL circuits next time on Monday. So let's end it here and work on the homework assignment, prepare questions, think about the material, think about the conceptual questions. And on Monday, we're going to finish this chapter and we're going to start chapter 24, electromagnetic waves. So